The next point I wanted to make has to do with the Pythagorean theorem. And I wanted to illustrate for you a way. There are incidentally many ways of proving the Pythagorean theorem. I happen to have my handy-dandy little triangle here. Let me draw it for you. Here's a right-angled triangle, like so. There. Let me close off my... There, I've closed off my little angles. And I'm going to call the small side A, I'll call the larger one B, and this longest one here we will call C. The C, as you all will remember, the technical word for this is the hypotenuse, right? It's the Greek word for the line that stretches out underneath. And I very cleverly put my right angle up here so that it does in fact stretch underneath for you all. Now you'll recall what the Pythagorean theorem claims, which is that the square of the angle A and the square of angle B will add up to the square of the hypotenuse C, right? And I think you've probably seen this drawn in textbooks. The Greeks don't think about this again in terms of algebraic equations. They think about them rather as shapes. So you'll have to pardon my little freehand drawing of a square. So this is the area of the square formed off of side A. And this is the area of the square formed off of side B. Not really, more of a rectangle there, isn't it? But you get the general idea. Numbers, incidentally, for them are ideal. Nothing in nature is a perfect expression of a number, but are limited expressions. And then the two of these combined, make it long enough, give you the square, and you'll recall our squares before, give you the square of side C. So A squared plus B squared equals C squared. That familiar? So that is the Pythagorean theorem. Now, how do you prove something like this? You can go to Euclid for a certain kind of a proof, but I'm going to try and prove it to you just using shapes and playing around with shapes. And this is probably where geometry begins, with this kind of play. So let's start off. Here's my little triangle, and I've made some squares that I hope are about the right size. So I'm going to start by taking the right angle triangle and putting the right angle in the corner of every square. So let's do it like this. Whoops, that didn't work. So there's one. And there's a triangle right there. This is side C, as you'll see, right? So let's do this again right here. Whoops. Not as tidy as I would like it to be. There's another one right there. Again, side C, all the hypotenuses here. And I'll do it again down here. And again over here. And what you, as you can see, what I've managed to give you are four triangles inside of a square. All of them here, here too. And what we have is the hypotenuse showing to the inside in both cases, which gives us effectively an empty square in the center of our square, which amounts to the square of the hypotenuse, right? Now, we should be able to play with my little triangles. If I take four triangles and put them in an E-shape, way, shape, or form inside of this box, I'm always going to have the same amount of empty space, right? That just stands to reason because they're all the same size. So let's see if you play around with this a bit, what if perhaps we could come up with some interesting locations of allocations of space. So let's put that there as it was before. And this time, let's see if I can do this right. We'll put that there. And then we'll put this one down here. as it was before. And then we'll do this one here like so. So I've simply taken the same 4 triangles and I've reallocated them in the same space. What you wind up with, left over, this is side B, and this is, this is side A, and this is side B. What you wind up with then is the same amount of empty space, but now reconfigured as the square off of side A and the square of side B. In other words, the same amount of empty space as you see with the square of side C, just reconfigured now as the square of side A and the square of side B. So that's an example of how you can prove the Pythagorean theorem really by just playing with the shapes. And a lot of what the Greeks seem to have done began with this kind of playing with the shapes.